Have you ever wondered how language models can generate human-like text? Or how speech recognition system can understand your voice commands? This video will take you on a journey through the fascinating world of probabilistic language models, neural Turing machines, hierarchical reinforcement learning, multi-agent reinforcement learning, and hidden Markov models. So let's get started with understanding what is probabilistic language models. Basically, probabilistic language models are mathematical models that assign probabilities to different sequence of words. Now, these models are designed to capture the statistical patterns in language, such as the likelihood of a particular word following another word or the probability of a specific sentence being grammatically correct. And by doing so, probabilistic language models can generate coherent and contextually relevant text. At a high level, probabilistic language models are based on the idea that words in a sentence are related to each other through their context. For example, the word bank might have a higher probability of appearing after the word financial compared to after river. So here the probabilistic language model captures these relationships by learning the joint probability distribution over the words in a sequence. Probabilistic language models can be used for various natural language processing tasks such as language modeling, text generation, and language translation. They provide a way to measure the likelihood of a given sequence of words, which is useful for tasks like language generation, where the goal is to generate text that is both fluent and semantically meaningful. In practice, probabilistic language models are often implemented as recurrent neural networks or transformer-based models. Now, these models use neural networks to learn the probability distribution of words and are trained on large amount of text data. To summarize this, we can say probabilistic language models are mathematical models that assign probabilities to sequence of words, capturing the statistical patterns in language, and they provide a way to measure the likelihood of a given text and are used for a variety of NLP tasks including text generation and language translation. Next comes neural Turing machine. Now this neural Turing machine are a type of neural network architecture that combines the power of recurrent neural networks with the capacity of external memory, and they are designed to simulate the behavior of a Turing machine, which is a theoretical model of computation that can perform any calculable task given the right instruction. A typical Turing machine consists of a tape divided into cells, a tape head that reads and writes on the tape, and a set of instructions that dictate the machine's behavior. Neural Turing machines similarly have a memory component or the tape, a pointer to control the memory access, that is a tape head, and a set of operations that can be executed based on the input and memory content. In neural Turing machine, the memory cells are implemented using a set of trainable parameters that store information relevant to the task at hand. The memory cells are typically organized as the one-dimensional array similar to the tape in a Turing machine. Now this neural Turing machine's tape head is a pointer that controls which memory cell is being accessed, and these operations performed by neural Turing machine are controlled by a set of trainable functions which are learned during the model's training. Now these functions dictate how the neural Turing machine process and manipulate the information stored in the memory cell. And the key advantage of neural Turing machine is their ability to perform tasks that require long dependencies, such as reading and processing sequential data, and to store and manipulate information in an external memory. And this makes them particularly useful for tasks like machine translation, where the model must keep track of previously seen words while generating a translated sentence. So to summarize this, we can say neural Turing machines are neural network architectures that combine the power of recurrent neural networks with the capacity of external memory similar to a Turing machine, and they are designed to simulate the behavior of a Turing machine by using a trainable memory component and pointer to control memory access. The neural Turing machines are particularly useful for tasks that require long-term dependencies and the ability to store and manipulate information. Next come hierarchical reinforcement learning. Now, this hierarchical reinforcement learning is a learning method that organizes tasks in a hierarchical structure, enabling an agent to learn complex behaviors by breaking them down into the simpler subtasks. And this approach is particularly useful for sequential decision-making process, such as robotics and game playing, where the agent must navigate through a sequence of actions to achieve a goal. In HRL, or the hierarchical reinforcement learning, tasks are organized into a tree-like structure with high-level nodes representing abstract goals and the lower-level nodes representing more specific sub-goals. Here, the agent learns to map high-level goals to sequence of low-level actions by gradually refining its behavior through repetitive interactions with the environment. And the key idea behind hierarchical reinforcement learning is that learning complex tasks can be broken down into the series of simple subtasks. And by learning to achieve these subtasks first, the agent can more easily learn the overall complex task. And this approach is similar to how humans learn complex skills, breaking them down into the simpler sub-skills and gradually refining their performance. This hierarchical reinforcement learning typically involves two types of learning. First is the value-based learning. Now, this involves learning a value function that estimates the expected reward of taking a particular action in a given state. And this type of learning helps the agent understand which actions are beneficial and how to navigate through the state space. Then comes policy-based learning. Now, policy-based learning involves learning a policy that maps states to action. Here, the agent learns to select actions based on the value function and the hierarchical structure of the task. In hierarchical reinforcement learning, the agent is trained to navigate through the task hierarchy, refining its behavior at each level until it learns to achieve the ultimate goal. Now, this hierarchical structure allows the agent to learn complex tasks more efficiently, as it can focus on mastering simple subtasks before tackling the more challenging high-level goals. So, to summarize this, we can say hierarchical reinforcement learning is a learning method that organizes tasks into a hierarchical structure to enable an agent to learn complex behaviors by breaking them down into the simple subtasks. And by learning to achieve subtasks first, the agent can more easily learn the overall complex task. Now, this hierarchical reinforcement learning involves both value-based and policy-based learning to navigate through the hierarchical structure and refine its behavior at each level. Next comes multi-agent reinforcement learning. Now, this multi-agent reinforcement learning is a type of reinforcement learning that involves multiple agents interacting with each other and the environment to achieve a shared goal or a set of goals. In traditional reinforcement learning, an agent interacts with the environment to maximize its individual rewards, whereas in multi-agent reinforcement learning, the agents collaborate, compete, or form coalitions to achieve their goals while simultaneously considering the impact of their actions on the other agents and the environment. In multi-agent reinforcement learning, agents can adopt various strategies such as first cooperation. Agents work together towards a common goal, where each agent receives a reward based on the team's performance and the actions are coordinated to maximize the collective reward. Then comes competition. Here, agents compete against each other to achieve their individual goals while simultaneously considering the impact of their actions on the other agents. Here, the agent's actions and strategies may be influenced by the performance of other agents in the environment. Then comes coalition formation. Now, here agents can dynamically form coalitions to achieve specific goals, and these coalitions may change over time based on the situation. Here, agents may join a coalition to achieve a particular sub-goal and then leave it to pursue another goal. So, in multi-agent reinforcement learning, the interaction between the agents and the environment are more complex than in single-agent reinforcement learning. Here, the agents must learn not only how to behave optimally, but also how to coordinate their actions effectively. And to address this complexity, multi-agent reinforcement learning algorithms typically use techniques such as communication, negotiation, and coordination mechanism. Now, these mechanisms enable the agents to share information, coordinate their actions, and adapt their strategies to the changing environment. So, to summarize this, we can say multi-agent reinforcement learning is a type of reinforcement learning that involves multiple agents interacting with each other and the environment to achieve a shared goal or a set of goals. In multi-agent reinforcement learnings, agents can collaborate, compete, or form coalitions to achieve their goals while considering the impact of their action on other agents and the environment. Now, multi-agent reinforcement learning algorithms use techniques such as communication, negotiation, and coordination mechanism to manage the complexity of multi-agent interaction. Next comes hidden Markov models. Now, these hidden Markov models are mathematical models used in various fields such as natural language processing, speech recognition, bioinformatics, and image processing. They describe a sequence of observations or the measurements that depend on unobserved underlying states. The word hidden refers to the fact that states are not directly observable and we must infer them based on the observation. To understand hidden Markov model, it's helpful to think of them as a way to model situation where we observe the effects of a process but not the process itself. A hidden Markov model consists of components like set of states. Well, these are the unobserved underlying states that the model is trying to infer. In many applications, the states represent different situations, conditions, or categories. Then comes set of observation. Now, set of observation are measurements or outputs that we observe directly. For example, in speech recognition, the observation may be the acoustic feature of a speech signal. Then comes transition probabilities. Now, these describe the likelihood of transitioning from one state to another. They capture the probability of moving from unobserved state to another. Then we have emission probabilities, which describe the likelihood of generating a specific observation given a particular state. They capture the probability of observing a specific measurement when in a particular state. To understand hidden Markov model better, consider the example of simple coin flipping game. Here the states are heads and tail. The observations are outcomes of flipping the coin, either heads or tail. The transition probabilities describe the likelihood of getting a specific sequence of coin flips such as heads heads, tails heads, or heads tail. The emission probabilities describe the likelihood of observing a specific sequence of coin outcome given the underlying state. To summarize this, we can say hidden Markov models are mathematical models used to describe situation where we observe the effects of a process but not the process itself. Hidden Markov model consists of unobserved states, observations, transition probabilities, and emission probabilities that are used in various fields such as natural language processing, speech recognition, and bioinformatics. Thank you.